10th. People online, if you could confirm that you can hear me, I would appreciate it. This is CS797K. We're going to talk about, continue on our RAID discussions today. We're going to start talking about finite fields. Before we get into that, because we had our technical glitches last week, I'm going to go ahead and go through our RAID diagonal parity illustration again. We'll try to do some quick fail and unfail there. So first, before I do that, I want to do a note that we're going to do a homework here. And this homework is enhancing the RAID DP code that we have posted. So if I go to Jupyter, we'll pull that up. The RAID dp.ipython notebook file that we shared has code in there to initialize the data drives. And there's 3 different kinds of ways to initialize the data drives. You can initialize it where each drive is showing up power of 2 that drive is, incrementing values and just random numbers. And so the assignment is enhance that to initialize the data drives where every data block is initialized to its stripe number. Now this might sound difficult, but it's not. Why? Because in generate DP, we are in fact counting through every drive. We're initializing the diagonal parity from the data blocks, right? So you can steal this code, rearrange it, reverse it, as it were, to initialize the data drives. So basically, we're going to have a new method up here if the method is equal to, well, you pick your name for this initialization method. This is one way we're going to do the anti-cheating thing. If you all pick the same name, we'll get a little suspicious. Yeah. On the dump drives function now, the dump drives function is set up in here to dump the data as hexadecimal 2 digits with a leading 0 on every block of data, every, as it were, byte. So I want to ask you to go ahead and call that a method called short hex. So you would pass the method or the how or whatever argument to the dump drives and say, I said how, call it how argument. How should I display the data? I want the data displayed in short hexadecimal format, right? Or you can have a long hexadecimal format where you have more bytes. And I want you to make a short decimal version where you print it out as 0 padded 3-digit decimal. So every number is a decimal number. Instead of an F, you're going to print a 0, 1, 5, right? And of course, that can go up to higher values if you want to, and you can initialize it to 150 or something like that too. That's our new data. And then the third task is to add a new cell at the bottom of the program where we're going to create a new RAID volume. And if you want to change the one that's existing in there, I suppose that's okay too. But go ahead and initialize it to, what did I say here? 14 data drives and 22 blocks, and build it up and initialize with a diagonal stripe pattern, dump it in short decimal, and then see what the output looks like, okay? And of course, make sure you rename that IPython notebook file. So this is kind of an initial start on what I think is going to be a project. We've got proof of concept on loading Ubuntu Linux systems, virtual machines in South Dakota, of all places. And we can go ahead and use what's called the RAID ZFS file system up there and mess around with RAID algorithms. And so for the semester project, we're going to try to see how far we can get in actually implementing RAID diagonal parity on a virtual machine in South Dakota. And if it fails, we'll know that. Anyhow, but we're going to use this code to kind of build a prototype. And then, assuming that all is going well, we're going to try to implement it translate it to C as groups. So, yeah, and then implement it. Okay, cool. Now, that having been shared, any questions about the homework assignment? It's not necessarily the easiest one, but it's also definitely not the most difficult one. So I try to find a nice happy medium. So now the next thing I want to do is to go out here and do a RAID diagonal parity example. So in order to do this, I'm going to go back to my camera over here. And if I control the that's about as good as I'm going to get, right? All right. Maximize that. So people online, please let me know if this is visible or not. I'll try to check the chat, so on and so forth. So we're going to go ahead and do a RAID DP volume as our illustration from last time. How many data drives do you think we should put on it? Someone give me a number. 4, 5, 6? Let's do 5, okay? Five data drives, okay? And then there's a parity. And there's a diagonal parity, right? Oh, so how many blocks are there going to be in a diagonal stripe? 5 data drives. How many blocks in the diagonal stripe? 5, right? So it's going to be block 0, 1, 2, 3, 4, 0, 1, 2, and so on and so forth. And these will be the extents. And this, of course, is block 5 or 0, 6, or 1, and so on, basically, on whether we're in an extent or not. We're going to focus on a single extent. I need more space. That'll fit. Okay. So diagonal stripe 0 starts on drive 0, block 0. 1 starts on 1 block or 0, 1, and it continues on drive 1, block 1, drive 2, block 2, drive 3, block 3, drive 4, block 4. And we have run into the end of the extent, right? And the block on the diagonal parity is, of course, up here. Diagonal stripe 1, 1, 2, 3, 4. This is not a diagonal stripe. 1, 2, 3, 4. 1, 2, 3. 1, 2. 4, 4, 4, 3, 2, 3. Okay. Those are our diagonal stripes where the data lives on there, right? Let's go ahead and then say this is diagonal stripe 1, 2, 3, and 4, right? Okay, so now we're going to initialize our parity and our diagonal parity. So we got small, easy numbers to deal with. So what's the diagonal parity here? 1 XOR 2 XOR 3 turns back to 0 XOR 4. This is a 4, right? And now we're going to put a 0 in here as well. Well, what should we initialize those to? Let's call that 7. Pick a random value to initialize it to. So we got 1 XOR 2 XOR 3 turns into a 0, so we get a 7 here, right? And what do we get here? 4 XOR 7 XOR 1 XOR 2. That's going to turn into a 0, right? And how we have a 3, a 4, a 7, 0, and a 1. We get a 1 because 3 and 1 turn into 2, 2, 4, wait. 3 to 1, the 4, the 7. Yes, I agree. You're ahead of me. I just got to keep up with you. Okay, 2, 3, 4, 7. 2, 3, 4, 7. 2. Okay, so we've initialized our parity, right? Now we're going to initialize our diagonal parity. Block 0, of course, this is going to be easy. All these zeros, XORed with 4. I'm sorry, all these zeros XORed with nothing turns into a 0, right? Now we have all these 1s, and then it ends with a 2 down here, right? So that is going to be 1, 1, 1, 1, and it's just going to be a 2. And then we got all these 2s, 1, 2, 3, 4 2s, and a 1. It's just going to be a 1. So really, this is going to like be kept capturing the same information as in the diagonal parity because we're canceling out. I'm not doing this right. 1, 1, 1, 1. Yes. Okay. Yes. Good. Okay. 3, 3, 3, 3, and a 0, and then 4 and 7 and 4 and 4 and 4. So I got 4 4s. They cancel out. We get a 7 down here, right? Boy, I picked some easy stuff, didn't I? Okay, now we're going to fail 2 drives in here. Let's go ahead and fail this one. And say we'll fail this one. Okay. So now when we've got our drives failed, we have to ask ourselves which diagonal stripes are alive and which are dead. So we ask DS0, DS2, DS3, DS4. And is it alive or dead? Alive or dead, right? So diagonal stripe 0. Piece missing, right? Dead. Diagonal stripe 1. Piece missing, dead. How about diagonal stripe 2? It's alive. Because 2, there's 1, 2 crossed out here. This 2 is still here, and there's no 2 on here, right? Diagonal stripe 3, we're missing this piece, and we're missing this piece. This is dead, right? And diagonal stripe 4. Now, hopefully this is not going to rebuild, if I did my math right. This is alive, right? Because diagonal stripe 4 is missing this piece, and there's no piece on this drive for diagonal stripe 4. Okay? So we can rebuild from diagonal stripe 2 and diagonal stripe 4. Let's go ahead and do that. Diagonal stripe 4 is here, 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 and down 0, 1, 2, 3, 4. Okay? So we're going to rebuild by XORing those numbers together and put them in here because that's the missing piece. 4 XOR 4, 7 XOR 7. That's convenient. That turns into a 4, right? That was pretty straightforward. Now, since we've done this, we can now rebuild here, right? Through the horizontal parity. What's that going to be? 3, 4, 7, 1, and 1 is going to be a 0 in there, okay? Now, we have diagonal stripe 0 is alive, right? And diagonal stripe 4 is in fact optimal. Every piece is available in it now. So we can continue on diagonal stripe 0, right? This piece is missing. We can rebuild that 0, 0, 0, 0, and 0. Amazingly, it adds up to 0. Okay, and now we can rebuild this piece here off the horizontal parity. You've got 7, 1, 3, and 7. And we XOR 1 and 3, and we get 2, right? So far, so good. Now we're going to go ahead and say that diagonal stripe 2 Well, that was already alive, wasn't it? Hmm? So what can we reconstruct from diagonal stripe 2? Well, it's already optimal. How do we reconstruct diagonal stripe 1? And the answer is we can't. Okay, purposely check this value. Remember I said that the number of drives in this underlying RAID 4 must be prime. And how many drives do we have? 1, 2, 3, 4, 5, 6, right? 6 is not prime. Okay. So this volume here is unrebuildable. When these drives fail that are 2 apart like this, we suddenly run into the fact that 6 divided by 2, 6 can be divided by 2, and so there's actually 2 different chunks in here. So because these drives are 2 apart, I can't do the reconstruct. If they were right next to each other, it'd work, right? If they're 3 apart or 4 apart, it would fail. So this is a slightly different example from last time. Last time we had a volume with, I think, 4 drive blocks and 1 parity. And so everything went cleanly, no matter what 2 drives we failed, would succeed, right? How would we fix this? Remember we said we had to do? We had to make a fake drive. Actually, right here, we'd have to make a fake drive 5 and initialize it with all zeros. And now all of our data is different and everything's going to reconstruct differently, right? But it would successfully work. In our example, we could just, add another drive, right? What we're going to do in our actual example is we're going to, when you run this and it tries to initialize the diagonal parity, no, it's not going to do that. It's not going to complain. It's going to initialize it fine with no complaints. That's another step we're going to do in enhancing the program. Say, deal with a, volume size, the number of drives that is not a multiple of a prime number on that underlying volume, right? So we can't reconstruct this fully. That's the end of this example. Okay. Is everybody clear on what we've done and why it failed on purpose? Because I did that on purpose. I really did. I didn't just screw up. Right? I meant to do that. Anyhow, and again, the point being that we have to do this whole diagonal reconstruction. We start with diagonal stripe 4. We built here, and then, sorry, we rebuilt this one, and then this one, and then this one, and then this one. And we have to do that zigzag back and forth, right? And eventually, and if we have prime number of drives, that zigzag is guaranteed to go all the way through. If we have a composite number, it'll fail in the middle. All right, enough of that example. Any questions from the online crew? Any questions from the in-person crew? All right. Back here, we can turn the camera back on. So you have 2 copies to look at. And we'll see how clear that looks on our recording. Stop recording. And